Welcome, everyone. Good morning. Thank you for joining today's webinar. My name is Lisa Holmes, and I'm the Marketing Director at Royal Circuit Solutions. Today we are discussing high-speed materials and technology for flex PCBs. But before I begin, I just wanted to go over a few logistics. You should have a control panel in the upper right-hand corner of your screen. If you have any questions during the presentation, please use this panel to type them into the question box. We will try to answer the questions during the webinar, but we'll also have time for questions at the end. So now I'd like to go ahead and introduce our presenters. Our first presenter is Scott Kono. Scott is the president of Royal Flex Circuits. He has worked in the flex circuit board industry for more than 10 years. And Scott will be joined today by Bob Meyer, who is the Vice President of Operations at Royal Flex, and by Chris Hunrath, who's the Vice President of Technology at Inselectro. So now I'd like to go ahead and turn this over to Scott to get us started.
Okay, thanks, Lisa. Let's see here. Is that working okay?
Yep, looks great.
All right, good. Thank you, Lisa. Today we're also going to be joined from our team with Larry Ibarra, who's our Quality Assurance Manager, and also Omar Madrigal, who is in our engineering department. So the four of us will be here to answer questions and talk about our experience with high-speed flex and rigid flex products. Our company is called Royal Flex Circuits. We've been in the flex circuit business for about 35 years. We're part of the Royal Circuits family. Royal Circuits is in San Jose, Hollister, Northern California, and Royal Flex Circuits, we're here in Los Angeles in Southern California. Together, we have about 120 employees. We work on, our specialty is very quick turn, prototype, rigid flex, and rigid flex PCB. And our office here, our factory here in Southern California, again, has been specializing in flex and rigid flex for the past 35 years. We really cater to a full range of customer base, from the medical to military and consumer product. With regard to this specific topic, we've seen a tremendous interest from across the range, primarily from the consumer product and military, although medical as well has become more and more interested in the high-speed material and high-speed flex and rigid flex. For our company, flex circuit and assembly, really, I think how we understood flex circuits for many, many years was basically a jumper cable, a single or double-sided flex with some components put on. This is probably the best example, where our long-term customer, Motorola Simple Technologies, was one of our main customers, and they were manufacturing the scanners that you see in the Walmarts and across warehouses throughout the U.S., throughout the world. And our mainstay product was this flex circuit that had a LED, red and green LED lights, together with a beeper and a connector. So that was the extent of a lot of flex circuits and assembly for many, many years. In 2009, that all changed with the iPhone 3, where the iPhone really pushed the limit on flex and rigid flex design, introducing technology, Wi-Fi, GPS, and so forth. And we saw that across the board change from our customers, more and more interested in the high-speed GPS, RF technology, and applications. And of course, the packaging becoming tighter and tighter meant it was all related to flex and rigid flex. Today, as we go to from the 4G to the 5G networks, going from a 20 to 30 gigahertz world to the 40 to 70, 80 gigahertz level, certainly there's more and more interest in the high-speed flex and rigid flex, which is something we would like to share with you today. Some of our experiences. We've got Chris Hunrath from Inselectro that will be talking about his experience and knowledge, which is quite extensive. And I think the first thing we can do is probably talk about one of our builds that we did. And this is also true with us, is that on the rigid flex side, that the other limitation that we've seen in the traditional sense is that we used to be able to use various connectors for board-to-board connections. Recently, obviously, we use zip connectors and other connectors across the board, but because of the high-speed constraints, we've seen the natural progression to the rigid flex is the only way to transfer data with a minimal amount of loss. And whether it's a large rigid flex to a small, very compact rigid flex, we've seen that industry change dramatically over the last several years as well. I think at this point we'd like to go through some of the examples that we have. Two examples. One is a flex circuit, and the other is a rigid flex. So I will turn it over to Bob in terms of how we, some of the things that we learned and our experimentation with this particular product.
Right here we're looking at a flex design we use with the Rogers material. It wasn't traditionally set up as a flex, but with the very thin cores, and it's a very pliable material, but it has real high-speed characteristics. Typically, it wasn't used in a dynamic situation where you're going to bend multiple times. It was a kind of bend-the-fit type application. We've done a number of jobs that have utilized this material and very successful in the high speed and the signal integrity requirements.
Yeah.
One of the options we do and when we run flex is we minimize any effect on the surface copper. We tend to put just an electrolysis to wet the hole. Then we do a barrel plate where we're only plating base copper in the holes themselves. So we've minimized any topography that would reduce signal integrity or loss. So this material is very functional for that. It's the number of units we've built, we've had only positive feedback. We also used a liquid photoimageable flexible solder mask because that has helps the signal integrity as well. That's an example of that build.
Yeah, this is the actual product, which had a very, very strong result in terms of the final bend, and the fit worked very well for our customer. Kind of give you the example of the actual flexibility of a high-speed material. In this case, I believe it was a 4 mil core. Is that right?
Mm-hmm.
And Omar, maybe you could explain. You actually had the impedance. I believe you calculated out at 100 ohm. Is that correct?
Yes. So the only thing we need to do is just set up the cores and the decay, and with the right trace width, we can pretty much meet any impedance that you might require.
Okay. That's an example of our flex circuit in the high-speed material. I guess the next thing. Oh, were there any, processing challenges that we had with this? Because it is a very delicate material.
Well, LCP, the fact that we handle lots of thin flex as it is, we do as low as a 0.5 mil core thickness. So the methods we use with framing and using carriers and such through the process, we minimize any effect. It is very susceptible to folding or damaging through typical equipment, but because we run, like I said, we run a lot of flex materials, we have the handling techniques to minimize any effects in processing. It's flex and real thin cores take special handling
right
in any shop.
Okay. Recently, another job that we had is this rigid flex. It's a 7-layer rigid flex, and you could kind of talk about how we process this.
Now here's a fairly common construction that we see. If you notice, the top layer is a 4350B. That's their high-speed layer, RF signal, and they're looking for high speed on that layer. And so what we've done is we've built it traditionally with our standard no-flow prepreg, standard flex, our AP material, which is the bread and butter of most rigid flexes. The 4350, it definitely gives you some good, much better electrical properties than standard FR4s, but the benefit is it processes just like a standard epoxy. So we're able to go through our normal hole prep, plating, and wet processing without any special handling that's required in PTFE type materials. So that's why the 4000 series of the Rogers is very popular in a rigid flex construction and even on rigid as well and supporting materials. We can predict the movement and it's very stable working with the other materials, the APs and the other FR4 materials, so it matches up real well.
Okay. This is the example of that particular project,
right?
Which was for more of an aerospace application.
Right, and you can see it's got two connectors on each end, so that's mounting into another, and then it's going to be carrying a chip there. You know, gold finish, which is fairly typical, and again, we do plate because it's on the rigid area. We will plate the surface, but on occasion we will do the same type of plating we do for flex, where we only plate the pads in the through holes. On this application, we plated the whole surface and pattern plated like a typical board, but we do them both ways depending on customer requirements. A lot of times the antenna boards that have a lot of, you know, that they require, you know, as pristine copper as possible on those traces. So we go to, I guess, great pains to keep the surface topography at a minimum. So it helps increase the speed. Yeah, okay, very good. You know, for us, when we put together a flex, a rigid flex, where we always have the question from our customers, okay, which material is best? And it really depends. Each application is different in terms of their end use application. So, but in general, for us, we always have a question of whether we're going to use the Rogers, Panasonic, or the DuPont material for the most part. Right. For the high speed. Or the Matrix is the Panasonic. Yeah, Panasonic. Yeah. So we've had experience with all of these and are very favorable to them for different applications. Recently, I know that our Rogers, the one that we use here, which is the Ultra Lamp, they're not making it this year, but they plan to restart it, and we're experimenting with using the Rogers 3003. In place of that is some of the ideas, only because there is no glass and it's a ceramic product, so you know, the ability for flex circuit and the integrity seems very, very strong. We have used the Panasonic Megtron 6. I don't know if you want to talk about that in terms of the construction. Yeah, the Megtron 6 is becoming more and more popular in that type of application. It does have a little more processing handling issues, but you have to, again, it's very, I guess, fragile material. So we use the different bonding plies with it. So we've used the Hitachi's no flow. We've also used the Meg 6 prepreg itself that they require. It does take additional, you know, high pressure to get the proper bonds, specialty press cycles, heat rise, that type of thing. But we've profiled that material pretty well, so it runs good. It does take special hole treatment and prepping to get your electrolysis and plating in the hole. We do have processes for that, so it does work. It does take a little more processing time to make it function properly. And then our third category, I guess, Chris, are you on the line?
Yeah, can you hear me?
Yes, we can. How you doing, Chris?
Okay.
And,
yeah,
we can go over the Pyrolex products, and Chris Hunrath from Insulectro will be taking over that area. So go ahead, Chris.
So the DuPont product line for Flex is based on polyimide film. Basically, Kapton is the base material for Flex circuits. Kapton has a pretty good XY stability for a non-glass reinforced product. So it's the foundation for Flex, as most people are aware. And these are all the different products here. Certainly, if someone needs more technical depth in these, you can reach out through the Royal Flex folks, and I can get you what you need. LF and FR acrylic adhesives have been the mainstay. They're very flexible. They're very sticky. They are more lossy. So for high speed, people are looking at some other options. You know, for high speed signals. And with rigid flex especially, when you have low loss and high speed materials in the rigid sections, you don't want to give up that performance into the transition between the between the rigid sections in the flex area. So we have a couple of different options. Again, the AP actually is a pretty low loss material all by itself. It's the adhesive that's used in the bond ply or the cover lay. And one option is, of course, to use the solder mask that Bob had mentioned earlier. Another option would be to use the HT or TK bond films. TK is Teflon Kapton. That's what TK stands for. HT is actually a thermoplastic polyimide film. Both have low loss characteristics. I don't know if you want to go to the next slide. You'll be on this one. So the HT bonding film is actually kind of interesting. So I don't know if most people are aware, but the AP has a Kapton core and then a very thin thermoplastic layer of polyimide, still very high temperature. It's laminated in an autoclave at very high temperatures to bond the copper foil to the Kapton. What DuPont has done is they've extruded this film, this thermoplastic polyimide, as a free film, and it's opened up, a lot of possibilities. It's much lower signal loss than acrylics and FR4. It's a whole different class. It's very high temperature. It has the highest operating temperature of any PCB material other than ceramics at 225 Celsius. The only trick to the HT bonding film is the lamination temperature is high. It's 600 Fahrenheit. Actually, the part temperature is 590. And then the Royal Flex folks have a method of achieving that. So they can build boards with this film. But it can be used as a cover lay or a bond ply. So you can use it in a multi-layer flex, or you can use it simply as a cover lay to protect the circuits. It's got, like I said, it's got very good loss characteristics. Not quite as low as like a Rogers 3003, but pretty close. Low moisture absorption, and and it's flexible. Next slide.
Okay, and we would like to invite our audience. If you have any questions at any time, please feel free to type in on the chat room any questions that you have, and we can answer questions on the fly. Okay.
This is the Pyrolux TK material. It's just showing a cross section. So different than the HT film or the AP film, where you have a thin thermoplastic layer of polyimide bonding the copper foil to the core Kapton. What you're looking at in this picture is copper foil, going from the top down. That's the light area, very light area. Then you see a layer of Teflon, then a layer of Kapton, then a layer of Teflon. So in this case, the Kapton is performing the same function as fiberglass. If you made a board out of pure Teflon without any filler or reinforcement, it would be very dimensionally unstable. It's very soft. Teflon actually cold flows at room temperature. So that's why all these different materials, 3003 and the like, they have different things in them to help with the XY stability. In this case, DuPont has made what we call a laminar composite, where they have a layer of Kapton in the middle that provides the XY stability, but the Teflon provides the really low loss characteristics. A little different, it's high temperature lamination than the HT. It's a little harder to work with from a fabrication standpoint than the HT, but it is lower loss and it's very flexible. So if you need a lot of flexibility, if you need to be really thin, TK provides these benefits because its low dielectric constant allows you to get match a particular impedance at a very low thickness and without making the trace extremely small, and that provides some better flexibility and bendability. And I have a little bit of data on that we'll get to. Next slide, please.
Yeah.
So this is showing HT versus AP and LF. Now, HT comes as a clad, but you can also use HT bonding film with AP clads. Nice thing about that is Royal Flex has AP inventory, and so if they wanted to build a part with the HT film, they could use the AP cores. Only downside of using AP is your operating temperature will be 180 Celsius versus 225 Celsius. But, being very familiar with the rigid materials, most rigid materials are rated for continuous operating temperature somewhere between 120 and 150 Celsius. So 180 is still way above most materials in the market today, and 225 is for those special applications where, let's say, you're putting electronics in an engine compartment or some aerospace applications, downhole applications. That's where you'd want a pure HT build. Really, the point here is you can see there's a substantial loss difference. Those two charts are scaled the same, so you can really see side by side how much better the HT is compared to the LF acrylic. Again, the acrylics have a lot of advantages. I mean, great shelf life, great flexibility, but the downside is they are lossy. They're not quite as bad as a lead-free phenolic FR4, but not nearly as good as, say, something like a Megtron 6 or Rogers, where the HT is much, much closer to those high-performing materials. It's actually somewhere between 3003 and Megtron 6 in terms of loss performance. Next slide, please. Just going back to the TK, you can see the dielectric constant's quite low at 2.4, very low loss, very good peel strength, very low moisture absorption, a lot of good properties. It's just because the TK Teflon melts at 550 Fahrenheit, the core has a higher melting point, but they're pretty close. So it's a little bit trickier to laminate, but versus the HT is pretty straightforward aside from the high temperature. But it does have some pretty nice electrical and mechanical properties. Next slide, please. And just a signal comparison between AP, Rogers, and TK. And you can see the TK is very, very low loss. It's a low loss material, especially at high frequencies.
Okay.
Next slide. So one advantage I mentioned is that the TK is very flexible. So there's some applications for high dynamic flex. Because it's low modulus, it doesn't provide a lot of resistance to bending. Again, also you can make the same electrically equivalent structure thinner. Both things help with flexibility. And this is just some loop stiffness testing done by DuPont to show the fact that the lower modulus does provide an improved bending characteristic.
Okay. All right.
Any questions? Yeah. Sorry. Go ahead.
Yeah, we'd like to open it up to our audience to see if there's any questions on flex, rigid flex, anything related to high speed or any other topic we're open to. We've got our panelists available.
Oh, peel strength.
Peel strength.
Yeah. You want to read that, or?
Should I read that? Do you want to?
Yeah, read that. Yeah.
Okay, our first question comes from an audience. The question is, do we have any experience, any peel strength issues with their Rogers Flex circuit? So I guess in terms of our experience with the Rogers, any experience with the DLAM or anything like that?
Generally with the Rogers, any of the high-speed materials, you tend to have a little bit lower peel strength. It's just part of the nature. I know with some of the 4350s and that type of material, they actually will go to a low profile copper on a foil, so it will affect the signal less. But generally, we haven't seen much separation or peeling. There's applications where they've tried to actually fold it or put a crimp in it, and that sometimes can cause the cracking and peeling. But generally, I mean, it is reduced. You got to watch your heat rise on your assemblies and that type of thing a little closer.
Right.
And baking is very important because that material generally can. Other than the HT, I think is right, Chris, it has a lot less moisture absorption.
Yeah, I think the second question here, Chris, is what is the minimum peel strength that's acceptable for high-speed applications? I don't know, Chris, you want to weigh in on that one?
Yeah, so it's interesting. In the rigid world, People are accepting for smoother coppers, or what we call VLP, HVLP, VLP2, low profile coppers, which are good for high frequency. People are accepting 2.5, 3 pounds on field strength for internal layers. They understand that there's a trade-off in peel strength versus the high-speed performance. Of course, the advantage is in an internal layer in a rigid board, you're fully encapsulated. If it's a single layer, not an issue because it's it's surrounded by epoxy that's all or some other resin, thermoset resin that's all bonded together. As long as you don't have delaminate assembly, everybody's happy. Flex is a little different because you're putting mechanical stress on the parts, and so you do need higher peel strengths. The other caveat is the layer you're going to assemble to, right? So wherever the components go, that has to have higher peel strengths. Really, we like to be above 6 pounds. Certainly no less than 4, but 6 pounds seems to be a pretty good number to work with. Now, AP out of the box tends to have, in excess of 12 pounds of peel. So 6 pounds is quite a bit less, but it's still a lot higher than what you'd see on rigid boards. So I don't know if that addresses the question, that you were looking for, or the information you were looking for, but that's what we see out there.
Yeah, again, if any of the audience wants more specific information on peel strength, you can email us and contact us, and we can send you the more specific information on all the different materials with regard to that topic. It has come up before, obviously, because of the construction and the challenges of high-speed materials. So that's something we can send out directly. Our next question is it possible to have a RO Rogers 3003 board, which is backed by FR4, connected to another 3003 board, which is backed by FR4, and the connection between the two is the 3003 top layer as a flex? So maybe if you want to try to do that one, Bob.
Well, we've built similar designs. We've had a couple where we've actually used the 3003, a real thin one, as the flex. It tends to be in a bend to fit situation. Typically, when you put a flex on an outer layer, we've done it. It just creates a little bit of manufacturing issues where the pockets are, and you get some dip down and compression. But we have different techniques to minimize that. So to answer that question, that we have done that, it takes some special processing for the plating and stuff for the holes, but it's been suggested directly by Rogers as a replacement on a few of the LCP builds that we had looked at. So 3003 is on the thin core, can bend the fit. They tend to say you want to warm it a little bit and then bend it and form it. We've done some boards where they actually mount to an aluminum part and they form it into a little curved area. So we've had a few examples of that.
Okay. The next question is, what is the cost of the AP versus the TK material? I don't know, Chris, do you have a general rule of thumb of the difference in cost? I mean, between the two materials, like a ratio, I guess, or general rule of thumb?
Yeah, the TK material is more expensive. I'm going to go out on a limb and say it's about 2x the cost of AP, but I'd have to verify that for you. So that's something maybe I can get back to you guys, and you can in turn get back to your customer.
Sure. Okay. That might be good. Typically the high speed is going to be a higher factor. I think that's pretty accurate, of at least a 2x multiple in terms of cost. And of course, the AP material has a full range from, if you look at the AP 911 versus a thicker core of AP 8545, that in itself could be over 2 times the price once you get to a 4 mil half solution. Mm-hmm. It could be twice the price of a 111, for example. And so, the price ranges are pretty extensive in terms of the multiples. And if you have exact, a stack up, we can give you more information with regard to those on a case-by-case scenario. All right.
Yeah, so looks like that's all of our questions for now. Unless somebody has any, you can continue to ask questions. Otherwise, Scott or Bob or Chris, do you have anything else that you would like to add before we wrap up?
No,
Yeah,
I
would like to. I'm sorry, go ahead.
Go ahead, Chris.
Yeah, I do want to actually mention to the audience crosshatch ground planes. There are advantages and disadvantages to that in Flex. The advantages of crosshatch ground planes are two. One is it improves flexibility for two reasons. One is it's less copper, but the other reason is it allows you to maintain a certain impedance in a thinner package. The other advantage is it's a moisture egress prior to assembly. The problem with a solid plane and Flex is once moisture gets underneath the copper, it takes a long time for it to come out. So assembly becomes much more challenging with a solid plane. So if you're building a strip line construction for the Flex area in a rigid Flex or even in a pure Flex, crosshatch planes offer some important advantages. Now, from a high frequency standpoint, there are concerns with when you have openings in your shield layer or your return path. I know Jonathan Weldon at DuPont as well as HD Pug has done some great work on analysis of this. They found that round openings in a crosshatch are actually better for high speed. It gets you a step function higher in high speed without noise and other issues. But if that's something of interest to the audience, we could certainly make sure Royal Flex gets the technical data and work with you on that. But it is a hot topic these days, is crosshatch ground planes. So I just want to mention that to the group. There might be some interest to the audience on that.
Yeah. Very good. Thank you, Chris. I guess from our side, we'd like to thank all of our participants from this webinar. Again, if you have any other specific questions with regard to this topic of high-speed Flex and rigid Flex, please feel free to contact us directly, and we will be more than happy to work with your individual construction requirements. Okay, and I think, Lisa, we're good to go.
All right. Thank you again for joining us today, and we'll see you next time.
Great. Thank you.
Thank you, Lisa.
Thanks, everybody. Bye.
Thanks, Chris.